This is what's going to be called a coffee cup calorimeter problem. And its problem statement says when 22.3 milliliters of 1.00 molar silver nitrate is mixed with 21.7 milliliters of 1.50 molar sodium chloride, the temperature of the mixture rises from 21.6 degrees Celsius to 29.7 degrees Celsius. The mass of the mixture is given here, and its specific heat is 3.94 joules per gram degree Celsius. First, write the balanced overall reaction for the reaction that occurred. And I'm going to go through that relatively quickly because that's not the main point here. But we know we have solutions with molarities, which means that those solutions will be aqueous because the silver nitrate is dissolved in water. This is a double replacement reaction, so we take the negative ion from one of them and pair it with the positive ion on the other. And the negative ion paired with the positive for the other product. And checking our solubility rules, anything with either sodium or nitrate will be soluble, which means that it will be aqueous. And while most chlorides are soluble, silver chloride is insoluble. It will form a precipitate, and it will therefore be listed as solid there. So that's a little bit of review. We do need the balanced reaction for this process because we have both the volume and molarity of two different reactants. So this is a limiting reactant problem. And we will need to figure out how many moles of product we can make. Part B says, calculate delta H for the reaction you wrote in Part A using the data in the problem statement. Your work counts for this problem. Please show all of your work. And what will happen is you will get different amounts of the milliliters for this when you do the problem, or most likely anyway. So this is from the lecture outline, a coffee cup calorimeter problem with reaction. And it goes, so the basis equation is that Q of the reaction equals minus Q of the solution. And this basically says Q, lowercase q, is the heat, says heat of reaction. And in this case, the heat of reaction given off, or sorry, the heat, just the heat given off by reaction is taken in is equal to the heat taken in by the solution. Okay. So Q is just a heat. It will have units of joules, and basically heat given off by reaction is equal to heat taken in by the solution. And the minus sign just means that one thing is taking in heat and one thing is giving off heat. Technically, we could put the minus sign on whichever side we want, because the minus sign just means there's a difference in direction of the heat. The minus sign just means that there's a difference in direction of heat. Okay. So from the lecture outline, Q sub reaction equals delta H reaction times moles reacted. So, there's my minus sign. And Q solution equals mass of solution times specific heat of solution times, well, it's delta T, but delta T equals T final minus T initial. So this last term here is also sometimes called delta T. But because we're actually going to be, we have a T final and a T initial, I wrote it out explicitly. Okay. Now, once we have this, all that we have to do is it becomes a chemistry word problem, and we have to take all of these numbers up here and plug them in. And what will always happen with this problem type is there will always be one thing we don't know. And this time, the one thing we don't know is delta H reaction. So we do have two temperatures, and it says from 21.6 to 29.7. So our T final is going to be 29.7 degrees Celsius, and our T initial is going to be 21.6. That one wasn't too bad. And reading along, the mass of the mixture is 45.9 grams. So that's going to be 45.9 grams. And the mass of the mixture is this, and its specific heat is 3.94. And I'll put my units, joules per gram degree Celsius. And what happens here is, so I said that Q was a heat, and Q will be in terms of joules. I have joules per gram degree Celsius, but my grams cancel here, and my degrees Celsius cancel here, so this does work out to have units of just joules. And there's only two numbers left. And so the next thing we have to do is find out the moles reacted, because delta H, it's telling us delta H is the thing that we need to solve for. So to find our moles reacted, we have to find limiting reactant. Find limiting reactant. And whichever one is the limiting reactant will tell us how many moles were reacted. So to do that, and I'll do that in red. So we find, okay, we have our volume and our molarity. We can find how many moles of product we make. 0.223 liters. We have 1.00 molarity, which is moles of silver nitrate per liter. Then it's 1:1 for moles of silver nitrate and moles of silver chloride. And we'll find our moles of silver chloride. We'll do the same thing with our sodium chloride. Where again, our coefficients for this are all ones. So mathematically, this last step you don't technically have to do, but just as a reminder that we're always looking for our smaller moles of product. That's what always tells us what our limiting reactant is. So now let me multiply these out. 0.0223 times 1, well, that's the easiest math ever, actually. 0.0223 moles of silver chloride. Then down here, 0.0217 times 1.5, 0.03255 moles silver chloride. We can see what our smaller moles are, and it is our smaller moles that we will now plug in. And delta H reaction is the only thing we don't know now. So let me just write this in, 0.0223. So we have all of our numbers here. I don't know why. These problems are very long this week. So let's see. I'll show that again in a minute, but so now let me write out everything that we have. Delta H reaction times 0.0223 moles equals minus 45.9 times 3.94 joules per gram degree Celsius. And the one thing I will do is I will actually do this subtraction. So 29.7 minus 21.6. So I get 8.1 degrees Celsius. So again, I can see that my grams and my grams cancel. My degrees Celsius and my degrees Celsius cancel. So my units on this side are going to be joules. And then when I multiply this out, I will end up dividing by moles on the right-hand side, and my answer will be in joules per mole. And so now let me multiply this out. So 45.9, and I'll put in my minus right here, times 3.94 times 8.1. I get 1465 divided by 0.0223. So joules per mole. So I'm going to just go back to 1465 minus divided by 0.0223. I get minus 65695 joules per mole. And I typically will put this in scientific notation or convert it into kilojoules per mole. And if you convert it into kilojoules per mole, it means that you move the decimal point 1, 2, 3 places over, and I get minus 65.7 kilojoules per mole as your final answer. Okay. So that's the end work. You've got your limiting reactant. You've got your delta H reaction. That's pretty much showing everything.
Excuse me, Professor.
Sure, Jumbo.
During the exam, do we have to convert it, or we can leave it at minus 65695?
Good question, Jumbo. So on your exam, and these problems are likely to be on your exam, so be prepared for it. I would expect this type of problem to be one of the 10-point problems so that I could look at your work for it, but something like this is pretty high probability. Sorry, here's your question, Jumbo. So how would you put in the answer? Well, on your exam, it would say, please input answer in kilojoules per mole. And so that's how you would know how to put it in. It would be clear.
Thank you.
Sure. Any other questions? Okay.
Please, sir, can I see the last page? Thank you.
Here's the last page again. Now, let me stop recording because I think we've got everything we need there.